Okay, so now let's get into what that means in practice. So I want to talk a little bit about trial design and what we're trying to achieve when we apply statistical methods. Okay, the first thing I want to emphasize, and I did emphasize it yesterday, is what is the question I'm asking? If I do not know what the question I'm trying to answer, I won't know what analysis I am using. And as I said, I have these students who walk into my office and dump the data there and say, analyze my data. And I say, what's the question you're asking? No, I don't know. Okay. And related to every statistical analysis, there's some of the ANOVAs, we'll get to the regressions and so forth. You are asking a question. You must have an hypothesis. Now, for some reason or other, and I haven't worked this out yet, statisticians like to use the term the null hypothesis. And basically, it's a negative of what you're trying to prove. I wish somebody would explain to me why. Okay. So in other words, I will test different cultivars for wheat rust resistance, but my hypothesis will be there is no difference between the cultivars. And I use the statistics to tell me I can throw out that hypothesis, and in fact, there is a difference. Okay. Now, I don't want to get technical on that. The point is simply, I'm using statistics to answer a question, and my question may be, is there a difference between cultivars? Or isn't there a difference between cultivars? And to me, that equals a null hypothesis, but it just makes more sense. Well, it's the inverse of that. Okay, won't go there. Okay, so in other words, with any statistical procedure, it's important to state the hypothesis of interest clearly, and note what I said here, before undertaking any statistical analysis of data. And I want to take that a step further. I want you to ask the question before you go and do the trial. Before you put a grain in the soil, ask yourself the question, what do I want to answer? Because the trial design you use for the different forms of analysis of variance, or for regression analysis and so forth, are different. And if I do not ask the right question before I start, and I come along with the data, I've got a mass of potential analyses. Which one do I use? Is my data, in fact, collected correctly enough to do one of those analyses? So I want to emphasize that point first. Okay? So before undertaking any activity, ask the question, set your hypothesis, and then plan your trial and your design and your analyses and everything, okay, so that when the data comes, you know what you're trying to do. Okay, so that's, to me, critical. Okay, so the kind of questions we might ask is, are there differences between treatments? And we will plan our analysis of variance and trial design accordingly. Are there interactions between treatments? Now, I might be doing a rust evaluation, but now I want to see if nitrogen has any effect on susceptibility. Okay? But the nitrogen can have a differential effect on the different cultivars. And I want to see if there's a significant interaction. In other words, if I put nitrogen on this cultivar, is it going to give me the same reaction as nitrogen on that cultivar, or is it going to make this cultivar more susceptible and that one more resistant? Okay? They're the kind of questions you want to ask. And for that, we use factorial designs. You asked me about temporal interactions. We have designs for repeated measures. We have genotype environment effects when we're looking at AMI analysis or something like that. So there are a whole lot of these, and I'll mention some of them. But I need to know that before getting started. And that's going to depend on my hypothesis. So I'm going to be like a stuck record on that one. Okay. We then get to regression and correlation, which we'll do later. And the question is there a relationship between variables or between multiple variables. In other words, does temperature affect the susceptibility to rust, or does it affect the rate of rust development? That kind of question. Is there a relationship between variables? And there are all kinds of specialized forms of these. We refer to disease progress curves, you have growth curves, you have prediction modeling, all kinds of specialized applications of regressions. And most of your prediction models are based on some form of regression or some network of regressions or whatever the case may be. So they form a very important part of the questions we are asking. And the goal of regression and correlation is what deductions can I make about the behavior of a population? Now, every population in the world, whether we like it or not, works on the principle of stimulus and response. Okay. Even we do. I drive down the road in my car and someone hoots at me and I get an itchy hand. I'm going to leave it there. Okay. The stimulus is he hooted at me. My response is I'm annoyed. Right? Stimulus and response. A plant growing in the field is responding to a stimulus. It's responding to nitrogen, phosphate, water, whatever the case may be. A pathogen is responding to the host plant. The host plant is the stimulus for the pathogen. If there's a resistance gene, well, then it's not going to grow that well. If there's no resistance gene, it's going to take off, okay? And we use regression analysis generally to look at stimulus and response and to look at relationships. So those are the kind of analyses that we're going to work through as we go along in the next couple of days.